stuff. For $10 billion in global trade is lost through the Arctic is increasing year on year. We also have a lot more, despite the progress that we've made with kind of the work that we're doing, we still get iceberg collisions, and they do cause extensive repair costs. And they also have a lot of environmental factors involved, crises like oil spillages, and sometimes even loss of life. So on average a year, we have about 2 to 3 iceberg ship collisions in the Northern Hemisphere. I'm not sure what that figure is for the Southern Hemisphere. But again, this is despite all the radar technology that we have on board ships. And we have other costs too. Sometimes ships are forced to divert routes, and that can then add on cost, because when you've got an iceberg in the area, obviously you want to avoid that area, but you might have to add on the added fuel costs. And yeah, that's kind of it for kind of like the commercial problems. We also have the scientific problems as well involved with the research and the science community. Right now, we've got satellites that are really good for iceberg detection. We've got L-band, we've got P-band. We're currently using Sentinel-1, so we kind of use a very kind of widely available. But in the future, we're going to be looking for satellites that have wider swath widths, because with wider swath widths, you get an extensive coverage, and you also get more frequent, not frequency, but for example, every time you want to get a picture, you get more available coverage. I'm trying to figure the term, but it's basically more radar images are available when there's more coverage of places. And so what you can do with that then is you can then download that data and use it for that purpose. So the latest research has actually shown, there was a paper released in this year, actually, I think. It shows that L-band is one of the better frequencies to detect icebergs. And that also corresponds with the work that I've been doing at PhD as well. We found that L-band was very good for detecting icebergs, especially in the Arctic. But unfortunately, L-band's not available everywhere yet. However, we do have some satellites. One of them is delayed at the moment, NASA's NISAR. But that's due to launch whenever, like, we don't know when it's going to launch. But we still have a long way to go in terms of like utilizing new techniques. So, for example, as you'll discover in this talk, nobody that we've spoken to so far kind of uses artificial intelligence or kind of deep learning techniques. It's in the research. It's kind of like a vague area, so there's a bit of a gap in the research. And sometimes we can get results that are not applicable in operational situations. So what I mean by that is, for example, let's say you have a really good detection system, and you get a result that looks great. It looks like it's a breakthrough and stuff, but you find that it's not good for operational purposes, especially if it requires a large computational load, or it just looks like it's very difficult to repeat. So that actually happened with an entropy detector that we did in the PhD. It gave us a probability of detection, but it also gave a very high probability of false alarms. And so as a result of that, it's not acceptable really for operational aspects. Okay, so yeah, that's kind of the problem side of it. But the solution that we've come up with, me and John and a few others at Lancaster, we have a commercialization team. We know that satellite radar works over a very large area in all conditions. And particularly for synthetic aperture radar, it can work in nighttime applications, and it can also work through cloud cover. And so it's very useful for remote sensing applications. So 3 satellite radar images from Sentinel-1 are provided. The idea is that will be provided twice daily by ESA, European Space Agency. And what we're doing is we're designing an artificial intelligence system that kind of automates the detection process, the iceberg detection process. And like the advantage of that is it's very low cost. And so that's also quite attractive to kind of commercial stakeholders. We only really have to worry about staff and computing, really. And we do have also got funding for a really big GPU system that we also have at Lancaster. Another thing that's really good, this system is not actually required to be installed on a ship. So on ships, you have like onboard radar kind of systems, you have onboard like navigation systems, but because this would all be done in-house at Lancaster, no equipment's actually required on the ship. So again, that saves cost, that saves maintenance, that sort of costs, that sort of thing. Yeah, and as I said, for researchers, more missions are on the way to being launched. Roselle, NISA, Biomass, etc. I just don't know when they're being launched yet. So yeah, I'm not going to go into massive detail on this. I'll let John talk about that. But this is the system that we're looking to use. It is basically a convolutional neural network, which is a deep learning technique. It's designed particularly for object detection in an image and then classifying as well. And so kind of the real, to be kind of as basic as possible, what it does is in every image, an object detection algorithm, it would look for anything in an image, let's say a cat, for example. If it thinks it's a cat, you can train data on that, and then it will tell you if you get like a test data and it has a picture of a cat, it will know then that's a cat. With a CNN, what it does is it kind of does a sliding window technique over. It does a convolutional technique, which is basically a sliding window. It takes the dot product of whatever the pixel value is on that image. And then it kind of like slides over, puts a filter over it for the whole of the image. And then, yeah, for what it's looking at is kind of region proposals. So a normal neural network, like I said, it will take any image that has like one object in it, like a cat. But this is designed for objects that are like, there's loads of different types of objects. You want to kind of find which one is the correct object. And so kind of the region proposal kind of does that. So it can then label the ice, if it finds an iceberg, and can label it, and it can give like a percentage value of accuracy, probability of false alarm, probability of detection, also called precision and recall. It really depends on which field of science you're in. So yeah, so more about kind of what we've been up to in terms of like the market and contacting stakeholders and stuff. We've had about 30 conversations in total with lots of different stakeholders. So for example, government contacts from Norway, Canada, Denmark, United States. You can see the flags there on the map. But yeah, we've had 30 conversations. Most of these were cold emails. We started cold emailing people just thinking, let's try, and if they don't reply, they don't reply. But actually, we had a really good response, and we actually got some good conversations going, some of them online. And then we also attended a trade fair in London back in March called Oceanology International. This is basically a massive trade show that looks at maritime technology, for example, like submersibles, that sort of thing. But we did have people going there that were from European Space Agency and a couple of other interested people. So we have got significant market interest in this potential iceberg product, mostly from, I think, government and private sectors. So one particular team that we spoke to was the US Coast Guard. Now, for those of you who don't know, the IIP, or the International Ice Patrol, those were the very people that got together a couple of years after Titanic sunk. So this is quite a significant contact for us, basically. A lot of the iceberg research field is only possible because, sadly, the Titanic sunk. And so, but yeah, what they do is they currently send up a plane. They send up a spotter plane every day. So they do like an airborne survey over areas that might have icebergs. And so we're trying to kind of gauge their interest in terms of what if we could reduce the amount of fuel and carbon emissions that happen if you have to go out every single day and map a large area of icebergs. What if artificial intelligence or our deep learning technique could actually reduce that requirement and in turn save on costs and stuff? And so that's what we had a conversation about, because sometimes they can't send these planes up. For example, geopolitics gets in the way. Right now, they have planes in different areas that are not necessarily involved right now in scientific data collection. And this is a private company called Rutter. And what they do is they supply onboard radar equipment to ships, so research vessels, ships, kind of any kind of sophisticated, also I think also normal shipping companies like NASC and stuff. I can't remember off the top of my head, but we basically met them in person as well at the trade fair. And they work extensively in the polar region. So they also have this ice navigation system. They're not using deep learning techniques either, which we found surprising because we thought, okay, they've got algorithms that can help us distinguish different ice bodies in water and stuff. And they don't use deep learning for it. So already we kind of get a sense that the commercial world is not necessarily utilizing deep learning and artificial intelligence at the moment. But what did happen is they offered us some sort of non-disclosure agreement to apply to test our system and to their ship-based data, basically. We don't know anything more than just that for now. We have yet to kind of follow up from our conversation, basically. Some examples of other organizations that we spoke to: European Space Agency, the commercialization team. They actually showcased our work as an example of observational scientists using their data. The pure aim for them was to show that commercialization projects with Earth observation was possible. We had calls with Canadian, Norwegian, Danish government ICE services. They were all very interested. None of them use AI or deep learning. We also contacted, I don't know if they're a government organization, but I think they're private, but the Sea Corps are quite, if you're interested in like iceberg detection and sea ice products there as well, there's Sea Corps in Canada that can give you information on that. And then in the private sector, we also had like a little startup company called Digital Earth Solutions. They're not like academic, they're more industry, but they still do like Earth observation kind of stuff, but they don't do icebergs right now. They work with people with oil spills, and they're based in Spain. But that was quite interesting as well. It's not just like government that was interested in stuff. There was less interest from the insurance companies. We did contact a couple of insurance companies. They tend to lag the industry in my experience, and they're also very risk averse. So by that, I mean, they're like not willing to, they say that we're too early for the market and stuff like that. They come up with these statements. One of the things that we did a lot of digital testing. We only had like 8 weeks to do this. So we put together like a little kind of website. It's called a landing page. It's just like one page. You have a look at the information on it, you decide, oh, this is interesting, I'm going to contact this person, or I'm going to come back to this or something. So we had some relatively good engagement there. And yeah, this was basically a LinkedIn kind of digital campaign. For those of you that do use LinkedIn. Yeah, there were a total of 372 visits, and there were 13 users that returned. So a relatively good level of engagement, despite kind of the niche sort of area. Again, the commercial world is quite hard to get your foot in when you've got quite a niche field. Now, we do have a little bit of competition. There is still very limited use of AI for this or other kind of related problems. But we did find that there are some Canadian researchers. So I spoke to people at the trade fair called Canada Ocean Supercluster. They were reluctant to give any more information about if they were handing out grants to people, research grants to people, or if they knew of any people that were working in this exact sort of area. So there are researchers that are in Newfoundland, Memorial University. I think the difference with us is we are funded by UK government grants. We aren't limited to a particular location. So John will show you images later from Franz Josef Land in the Arctic, but we're also not particularly limited, so we could look at other areas as well in the future, as long as, of course, it's in fast sea ice. But yeah, we're also improving an already existing technology that we know works. So right now we're at TRL5 on the market. TRL5 I'm not sure if you guys know how that works, but TRL5 is 3 or 2 levels away from being market ready, basically, in the business world. So what's the next steps? Basically, the next steps, we want to move on to what's called the IQ Explorer stage. So the IQ is like a training program. You go through like 12 weeks of a commercialization training, basically, and they just show you how to deliver a pitch to potential contacts, investors, or stakeholders who may be interested in your technology or your product. And so, yeah, the ultimate plan is to bring the system from TRL5 up to TRL7. That means it will be more or less market ready. It doesn't mean that we may have a very robust system by that point, but it does mean that as long as people start using the system, and we'll know that if we release a paper and someone else releases a paper later that's used our work, then we'll know it's got evidence that it works, and we can use that for market evidence as well. Continue improving the detection capabilities as well. So right now I'm working on the Python code for that. It's very tedious, but we'll get there. And yeah, continue working with these potential stakeholders. Like I said, I was very thrown in at the deep end when I started this job, and I'm kind of glad to be out of the 12-week program now and actually working more on the science. So hopefully we'll have a lot more results coming very soon. And with that, that's my part of the talk and over. And we'll have time for questions at the end, but I'm just going to hand over now to John. So thanks very much, guys.
Apologies, I'm swapping between. Okay, that's okay. Can everyone see that okay? Oh, yeah. I don't even use Presently. That's really annoying. Yeah, sorry, done that again. Does that look okay? Oh, is that all right for the people online? Do you reckon they can cope? Or
yeah, I mean, yeah, sure.
I'm sure I'm fine. It's not. I haven't got any comments on there or anything. Hi, I'm John. Good to meet you. Yeah, thanks again, Sonny, for that. Yeah, so I'm talking about detecting icebergs and galaxies with artificial intelligence. So obviously, Sonny was talking about the commercial side of it. I'm talking more about the detection side of it. There may be some sort of pictures from astrophysics in here, which I hope you'll all enjoy. Please feel free to ask me questions about astrophysics as well if you want to, but icebergs might be more relevant. So yeah, this is with me and Sonny, who's just given the talk. We've also got a PhD student from Cambridge who's working with us as well. And these people here have already worked on developing the algorithm and the commercialization stuff, but they've moved on. They all sort of had relatively short-term contracts. Okay, so we'll talk about galaxy clusters, and you'll find out what all this means. Then machine learning. So the reason why I got into machine learning was through using machine learning to find these objects called galaxy clusters. And then I'll show you about detecting icebergs. So that is a galaxy cluster. This is one of the first images. In fact, this is the first image that the new James Webb Space Telescope released. Just briefly go over it for you, but see the sort of, what kind of colours? Kind of beigey coloured things. These are the galaxies that are in the cluster. So these are massive galaxies that no longer form stars. They're all together in galaxy clusters, and they're very heavy, massive galaxies. These red things behind it, does anyone know what they are? Gravitational lensing. So these are galaxies very, very far away behind the cluster. We've been gravitationally lensed around the cluster, the amount of mass, so that means it bends light. That's kind of cool. And then these things here are stars in our own galaxy that are in the way, often known as rats of the sky, because they get in the way of actually being able to observe galaxies. But they do look nice. So a galaxy cluster is made up of hundreds to thousands of galaxies. They have a mass to 10 to the 16 solar masses, so 10 to the 46 kilograms. They have the size of up to several megaparsecs. So that's 3 times 10 to the 22 meters is a megaparsec. And despite being called galaxy clusters, galaxies only make up about 3% of them. Most of the rest of it is hot X-ray emitting gas. And then the majority is dark matter. Why would anyone want to find galaxy clusters? So they're excellent laboratories for galaxy evolution studies. You've got a group of galaxies that probably all formed at the same time. They're in a dark matter halo that you know the mass of. And so because of that, you can use them to look at how galaxies evolve over time. They seem to accelerate the evolution of galaxies. But also they're key probes of cosmology, so how the universe itself evolves, so how old it is, how fast it's expanding, all of that sort of stuff you can find out from galaxy clusters because they trace the largest dark matter halos in the universe, and you can see them out to very far distances. You can see them billions of light years back in the past or very great distances. So we will get onto icebergs and machine learning, don't worry, but searching for galaxy clusters, they're originally searched for by these two characters here. That's George A. Bell. Lots of galaxy clusters are named after him, so they're all called A. Bell and then a number. And this here is my favorite scientist, Fritz Zwicky. He's quite a character. Thought to be one of the first people to put something into space. He fired a gun at some velocity that got something into space. But what they used to do is eyeball monochromatic photographic plates to look for overdensities of galaxies. So they'd look here and go, oh, you know, that looks like a collection of galaxies, which we don't see down here, and therefore we think there's a cluster there. So that's no longer the case of what people do anymore. Instead, we look at X-ray images. There's lots of hot X-ray emitting gas in these things. So if you see an extended X-ray source, then you know there's probably a galaxy cluster there. Or also, alternatively, instead of looking at images, we have data reduction processes that basically draw circles around all the galaxies in the image, turn that into a catalog. So each of these circles will describe a brightness and a color of a galaxy, and we can look for features instead in this space here, which is basically how bright a galaxy is and what on the x-axis and what color it has there on the y-axis. So people don't tend to eyeball images anymore to look for these things because there's just so much data covering the entire sky, you couldn't do it, and it's very deep now. So you've got, you know, you've got detail out to very large distances. It just wouldn't be possible to do that. So what we tend to do instead is find candidates. This here is an X-ray image. This here is supposed to be an extended X-ray source. We're not quite sure, so then we look instead at an optical image of this region, and it is something that looks like a galaxy cluster. So you can say, oh yes, this candidate is telling us that there was a cluster there. Then we looked it up, and indeed there was. So this is where the artificial intelligence comes in. If you have to eyeball all the candidates anyway, why don't you just look for clusters in the entire sky using artificial intelligence? It wouldn't be possible for a person to do this because it would take forever, but it is possible to get machine learning to do it. So you break up the sky into cells and look across the whole sky and look to see if we can find them. So I came up with this idea, and I thought we would, you know, basically using machine learning to recreate the work of Abel and Zwicky. And so this algorithm was developed by Matthew Chan, my former PhD student, and it was based on the faster RCNN CNN that Sonny showed before. So it's a region-based convolutional neural network. So this is a neural network. In this case, it's an ANN, an artificial neural network. You have input layers. That could be your image. These could be pixels in your image, for example. You have hidden layers. This is where essentially the thinking is done. And then you have an output layer here that gives you a classification of what it thought these pixels were in the input layers. An example here, which I actually got from Wikipedia, On the left there, you're training a model. So you're showing it starfish, and it's associated, the model itself has a hidden layer that already knows about certain features. So many of these CNNs know about certain features. For example, in this case, it knows about the star shape. It also knows about bobbly texture. And so it associates those starfish with a star shape and that bobbly texture. It associates these sea urchins here with an oval shape that it knows about and with a stripy texture. And so once you've trained your CNN such that it knows that these things are generally associated with these nodes and these things are generally associated with these nodes, you can then apply that to an input image. And so, sorry, this isn't, well, a neural network in this case, but it would also apply to a CNN. So here's your image of the sea and the sea floor, and you've got your starfish there. And again, it's associated with the star shape and the textured node there. And so it knows this is definitely a starfish. But then here you've got a snail shell. It looks a bit like this oval perhaps, but not very much. So it gets a much weaker signal. So it says that, you know, there are thresholds involved as to what you might decide would be the threshold for a detection. But it's decided here that that starfish is a starfish, and it's decided here that this may have some properties of an urchin, but it probably isn't. It hasn't given a huge amount of power to that there. The convolutional neural network is similar, as Sonny was saying, but what happens is you reduce the information, because if you had 100 by 100 pixel image, you'd need 10,000 nodes in your hidden layers. And that's too much. So what it does instead is it slides a window across the image and performs a convolution to find features. It then essentially pulls them down so that you have smaller images going into the effectively smaller images going into the hidden layers. So for example, here, this is an edge detection convolution. So you've got an input image there of fruit. And then after you've applied this left-Sobel convolution here, it essentially detects the edges. And so there's less information here. Now, what it does then is the pooling that reduces the resolution of the convolution, for example. And so it does that hopefully without losing useful information, and it passes it to the nodes. Now, there are checks and balances that can basically backpropagate to make sure that you don't lose too much information in that stage. What you're trying to do is reduce the amount of information that you're feeding to the hidden layers. Yeah, I've already said that about the 10,000 nodes, but then you can see it then goes on here to the hidden layers, which are fully connected to each other with the nodes, and then it makes a decision as to what it is, and it gives you a percentage value or probability of what it is, and presumably in this case it would hopefully think this was an image of a bird. Sonny's already shown this. There's a slight difference between faster RCNN or RCNNs and normal CNNs, and that it also proposes regions as well. And so for an example, this would be your sort of classic CNN. You show it a picture of a cat, it says cat. This is what faster RCNN can do. You can actually do this on video as well. So you can actually live have a video where it's detecting things all at once. It's very cool when you can see that up and running. So it knows there's a dog there. It's interesting, it gets that dog at 99% there, but this dog here at only 70%, and that's because the dog is sort of turned away. You can't really tell, but it still has worked out that it's a dog. That's clearly a person. It's decided this is a handbag, etc., etc. It has a slightly lower probability of person for this person here, 80%, but perhaps it's because they're sat in front of another person, perhaps it's because they're sat down, that sort of thing. And then there's a crowd behind there, and it's getting various probabilities that these are people as well. So it's very good at image detection, object detection, sorry, in images, but also classification at the same time, rather than more classically with a CNN, where it would just do it on per image basis, where you show it the cat and it says this image is of a cat, basically. So last thing on galaxies, I won't show this for too long, but basically, actually I can't get it to work anyway. But oh yeah, there you go. So this is the thing where this would be, this is a GIF of how it works. It's looking for galaxy clusters. I think there's probably one there. And there you go, it finds it. So it's quite hard to see, but this is quite wide field images of the sky. And I don't know, maybe there. Yeah, okay, and there's one there as well, for example. So you find two examples of the same thing in an image. And it gives you this probability as well. So a location, the confidence score, maybe up there. Yeah. I did this talk showing about this. Oh, that's got to be one, surely. I did this somewhere else, and someone was getting the clusters faster than this, and I had to explain to them that this is a GIF, and this is not the CNN running live. This is just a GIF image. But they thought they were beating the computer. I suppose even if they were beating the computer, it wouldn't matter because you couldn't look at the entire sky as a human anyway, whereas this can. Okay, so I've sort of rattled through that just so I can talk also about the AI for iceberg detection. So we received a little bit of funding from STFC to hire an RA. It was James Edholm, who investigated whether this AI research from galaxy clusters could be applied elsewhere. There's a huge list of potential areas, agriculture, etc. But one of the potential areas was icebergs. And the idea being, climate change increases shipping at the poles, potentially an increased presence of icebergs. So there's a need for additional safety systems. And I was sort of looking through funding opportunities in general, just with a list we have in our department of different funding opportunities we can look at. And one of them was from Lloyd's Register, which is a maritime safety organisation. And so we got that grant, a relatively small amount of money, but I could hire an RA for 3 months to convert the galaxy cluster detection algorithm to an iceberg detection algorithm. And that was very successful. We based it on a paper that Armando was an author on, which is Soldal 2019, which used a CFAR, constant false alarm rate algorithm with a blob detector on images that have been iDPolRAD filtered. I'll show you that in a minute. And CFAR varies the threshold for detection of icebergs based on the noise level of the background in order to maintain a constant false alarm rate. Is that correct? That's my understanding of it. Yeah. So we thought instead of using CFAR, we would use AI on this. And so this was the data we used. The red there is the SAR data, synthetic aperture radar from Sentinel-1. The green squares there are the optical data from Sentinel-2, and this is over Franz Josef Land. It's the exact same data that Soldal used. There's no cloud coverage in these images. They're taken at the same time, and the icebergs are embedded in fast ice, so they're not moving. So it was basically taken at the same time, and even if there's a slight delay, there won't be a huge change in their positions. This is the example data. This is Franz Josef Land in terms of where the land is. If you look at the HH polarized SAR data, so horizontal wave going out, horizontal wave coming back. This is the optical data set. You can now see that all of this looks like ice, but actually there's land there, which you can sort of see there. But between it is this fast ice. This is about 100 by 100 kilometers on the side image, basically like one of those green images we just saw. But I think I've made it square instead. And then here we apply a land mask, so we're not trying to detect icebergs on land, basically. We're not training it on things that we think are icebergs that are actually on land. That's just from the Polar Geospatial Center. And so for the data processing, we use the DPolRAD that Armando uses. So you take the HH image and the HV image, the HV being horizontally polarized light goes out, but the reflection is vertically polarized. And we combine them together using this filter, this DPolRAD filter. It's the square of the HV in a test window minus the square of the HV in a training window divided by the square of the HH in a training window. And so those different window sizes, the test size is a smaller window size than the train size. And so you end up with this filter, and what happens there is you end up being able to see the icebergs much, much more clearly, and they stick out very brightly. You can also, we don't actually use the iDPolRAD now, talking to Armando about this. That's, you also times it by the intensity of the HV as well. So this enhances the icebergs relative to the background. This relates to whether or not the icebergs are wet or whether there's some scattering inside the volume of the icebergs, and makes it much easier to detect them. And you can see on that SAR image there, you can also see this is the optical image, and there's a group of icebergs there and several other icebergs around that are showing up on that SAR image. We apply these land masks, as you can see, if you look along the coastline there's things that you may or may not decide might be icebergs there, but of course it's on the edge of the land. And so we remove that coastline with the land masks. And then we actually go and try and label icebergs. These green dots here are vertices of a square, so don't look where the green dots are. It's the thing inside the green dots is where the icebergs are. And so that's us labeling. We label it by looking at the optical image and the SAR image at the same time, but only training the AI on the SAR image. So the CNN only sees the SAR image, even though when we're inputting it, we require it to have optical and SAR data that you can see the iceberg in. Now, there may be some bias that creeps in because of that, of course. But if we do it in such a way that we train it only on the SAR, then it can obviously be used in a wider range of weather conditions and lighting conditions. And so this is an example of predictions made by the model during testing, for example. So this is the ground truth, what we decide is the ground truth. Again, there's another bias there. Of course, that's what we've decided based on the images are definitely icebergs. We train on those, and then this is the prediction we get back. So these predictions here correlate fairly well, as you can see, with the ground truth boxes as well. Now, this here looks very impressive. There are caveats to it, but this is the precision and recall graph. For people who are not familiar with this, you want to be as far into the top right corner as possible. So have perfect recall and perfect precision. And here we're doing very well. Again, caveat to the various biases that have gone into this. Precision, of course, is true positives divided by true positives plus false positives. Recall is true positives plus divided by true positives plus false negatives. And there's something called the F1 score. That's 2 times precision and recall divided by precision plus recall. You want to maximize the F1 score to get you as close to that top right corner as you can. And when we do that, each of these data points here represent a different threshold for what the CNN thinks is an iceberg. And so the F1 score of 0.928 gets you as close to that corner as you can. That's on a confidence score of 80%. So when the CNN thinks it has an 80% chance that this is an iceberg, that's when you get closer to the top right corner there. So that's the one we choose. We can compare this to conventional detection. So our results are competitive with current iceberg detection algorithms, such as the one in Soldal, the CFAR, etc. The numbers sound impressive, but they vary. There's obviously biases have gone into that. We've decided that this thing has to be seen in optical and has to be seen in SAR at the same time. And so there's a bias there. It also depends on the size and resolution of the input image. If we use smaller images with higher resolution, we get better scores, and that there was using smaller images. When we get wider images, we're getting precision and recalls of round about sort of 80%, sort of that kind of value. Also, there's a problem of establishing the ground truth. We're getting a high precision and recall, but is this a complete set of icebergs or not, basically? It works well in fast ice. It seems to work in open water as well. It's good that it works in fast ice because obviously you've got that background of the ice there. It seems to work in open water. There might be problems in rougher sea ice. So when you've got sea ice with an iceberg embedded in it, and also in rougher seas themselves, when you've got large waves, etc., you may get problems then with the scattering. The sea ice is a problem because icebreaker ships and things can just drive straight through the sea ice, no problem. But if they hit an iceberg, that is a problem. And so if you can detect them within this rough sea ice, then that would be ideal. And that's part of the improvement we're going to make as well. Next steps, we've got Sonny has just started really working on the actual algorithm itself, having been doing the commercialization training for his first 3 months. We're further developing the software, so we want to train the model on a wider range of environments, not just fast ice, not just calm open waters. We want to try different CNNs as well into our model. There's a new CNN, well, relatively new, it improves every year, called YOLO, you only look once. And also we want to explore commercialization as well. And we're keeping our contacts open with various companies, such as the governmentals that Sonny was talking about, and Rutter as well. But that is basically it. Yeah, so yeah, hopefully our AI-powered system seems to work well. And then we want to further develop things, make it more general. And the ultimate goal is to test it in a live situation. We're having conversations about this. We're having conversations with the British Antarctic Survey. We should be able to talk to the crew about whether or not they've seen icebergs at the same time we're trying to detect them in the same area. And so because of that, we might be able to have ground truths for our detection. On top of that, we also have historical data from the US Coast Guard's plane as well that we can access. We haven't accessed that yet, but we could go back through ESA's data and also go back through the US Coast Guard's data from the spotter plane and see if we would have seen the same things that the spotter plane sees as well. So again, it's another opportunity to understand whether or not we actually have a ground truth that we can trust. Yeah, thank you very much. It's been great to come and talk to everyone about icebergs. Thanks.
Thanks, John. And thanks to Sonny as well. Does anyone have any questions? If anyone on Teams has any questions, they can raise their hand or stick it in the chat and I'll come to it, but I'll give privilege to those that came along today. So any questions?
Hey.
Yeah, how big is the icebergs that you're...
Good question. So in terms of the sort of resolution, we end up with a resolution of around 10 meters. And so I guess that's the answer. Whether or not we can also get essentially point sources that are below the 10-meter resolution but still see them because they're bright enough, that's possible. There's this sort of level of what size is an iceberg dangerous versus what size can we detect. And I think, there is still a great deal of danger in the things that are around about 5 meters in size, that you might, so if we had higher resolution data, maybe that would help. Sometimes these things move around in groups, so maybe finding a signal because there's a few of them together, or because you've got a 10-meter one near some smaller ones, maybe that's good enough. But yeah, I suspect that higher resolution would be an improvement.
And so can you actually see the icebergs in optical images?
Yes.
So
yeah.
That's how you were.
That's our ground truth. Yeah. So it's quite hard to see actually, but you've got SAR detection there, and you've got about 3 icebergs there in the optical there. So I guess in a way you've actually got multiple because they've got a slightly lower resolution after applying the filter. And also because the data itself is a slightly lower resolution, I think. But yeah, there are a few ones here that show up more clearly than others. So yes, there's potentially a bias there because we're already matching the ones that are optical and SAR at the same time.
Yeah. So you could look at higher resolution optical data and see if you get the signal on the SAR as well. Yeah,
definitely. At the moment, we're not restricted, maybe not the right word, but it's great to be able to just use the Sentinels just because there's so much data from the Sentinels and it's easy to get access to them. But maybe in the future with the NISAR and things like that, there may be other data we can use.
Yeah, you could look at Planet Labs for optical data as well.
Yeah, that sounds really cool. Yeah, who runs that? Is that? Okay, yeah, and is that free or?
Yeah, if you're a researcher, they have like a limited amount that you can download. You can get a research license.
Oh, that's cool.
Daily imagery at 3-meter resolution.
Excellent. Yeah, and optical or
just
optical? Oh, great. Yeah, that sounds really good. Thanks.
Still on that, if you want, well, the trick we use in house is, even though it's free, there's some limits. So the trick we use in house is that we have various, a number of our colleagues all have accounts.
Yeah. So there's a limit for one person, but if you needed.
I'll edit that bit out of the recording.
Okay, sorry.
Yeah, so that's what we use to get more data.
Oh, excellent. Okay, yeah, good. Yeah. Multiple email addresses. Okay. Yeah.
If you want to make it operation.
Yeah. What was the name again? Sorry. Planet Lab. Thank you. Yeah.
There is night.
Yeah.
6 months of the year you will get it. Another 6 months.
That is true.
Yeah, I think it's mostly for labeling, right? To guide you.
Yes.
Yeah. Once you get one clear date, which is good enough.
Yeah. Yeah. For labeling the SAR, really would be. Yeah. Exactly. Yeah. That's brilliant.
Okay.
Two questions. I think one is more technical. It's like what you've been using for the deep learning. Like, have you been using any of like more like remote sensing specific frameworks, or just been like pure?
Just pure CNN.
Or
Just pure CNN from TensorFlow. Yeah.
TensorFlow?
Yeah.
And the second one was like, I was interested, especially with somebody that's talking about like the commercial things, setting up the meetings and the scoping and stuff. Is that something that you do all yourselves, or do you have like support from the university to do the kind of outreach?
Yeah, so they were quite good actually. The university has a commercialization team. I don't know, maybe something equivalent here as well. And so they sort of keep us in check and make sure that we attend the meetings we're supposed to be attending with Innovate UK, because Innovate UK are part of the grant. And so we have to do various things with them, as Sonny was saying, this sort of 12-week course and things. But our commercialization team keep us on our toes. We sort of have a meeting with them quite regularly and things, just to make sure that we're sort of doing what we're supposed to be doing. So in terms of right now, we're okay. We're focusing now on the research, but they have various tactics and things that might help. And they even helped writing the grant proposal as well, actually, because there was a bit in the grant proposal about proprietary things and that sort of stuff, but then there was also a bit about commercialization. They knew the right words to say for that part of it, which is not my field at all, obviously. Oh yeah. Yeah. So it turns out, the third officer on the David Attenborough, the boat that people tried to call boat team at Boatface. It turns out, is doing some higher level sort of officer training in Fleetwood, which is a town near the sea, right near Lancaster. And so we've been in good conversation with her. She'd be giving us as detailed as Sonny says. So that's really good.
Yes.
There were news stories, I think it was last year, looking at tracking big icebergs around the Antarctic, which was obviously a concern for shipping. Could you not also track with this? So rather than always scanning and looking for icebergs every time you got a new image, could you not actually then build up, if I see something that looks like an iceberg, but then more than 1 couple of hours anywhere near, it can't be an iceberg. Could you not use that kind of?
Yeah. So there's two sort of things there. One, we could do some sort of statistical model to see if you can see points shifting in some sort of grand scale or something. I mean, they don't necessarily always follow the same pattern, but there are also some of the other companies we've spoken to, particularly Digital Earth Solutions. They have their own model, and the Norwegian ice people as well. They have their own models of the flow of water, ocean currents, and so a lot of the stuff they do is modeling how oil spills would move in certain areas and that sort of thing. And it's curious as to whether or not we could almost use that to help, as you say, track rather than just say this is where they are now. And as you say, also, potentially reducing false alarms by having things that only ever appear in one image, for example, that as well. But yeah, in terms of ocean current models, it is possible to do that sort of thing too. So it might be possible to bring that in as well. Yeah.
So John, I don't know if you know him. There was a guy in Sheffield. It was the journalist. Yeah.
Use my wife, for example.
Sonny Babek.
Yes.
They developed something called SAR, and he was tracking icebergs.
Yeah. Oh, cool.
With SAR. So
yeah.
I don't know if somebody's still working on that, but it would be interesting to contact the group.
Yeah, we could contact the Sheffield group. Yeah, that's a good idea. Yeah.
Any last questions before we finish up? We're just
If I can continue on the question about the size of the icebergs.
Yeah.
In the paper of Ingrid, Solder paper, she was saying that you cannot really see icebergs smaller than say 150 meters inside image. So you see the optical one, I go to the SAR, and most of them you don't see. Have you tried to see if your CNN is able to be better than human and see the thing where people cannot see it?
It's a good question, actually. I've not actually, yeah, it's a really good question. I've not actually measured the size of the things on the optical image to then see what it is. But yeah, it was on the sort of scale of tens of meters is what I thought we were getting, but it may well be that.
So SAR a bit less.
Yeah.
SAR,
Yeah.
optical, yeah.
Yeah.
No, but it would be cool.
Yeah.
Also, some of the false alarms is maybe because you don't select the point as a iceberg, but an iceberg is optical.
Yes. Yeah, exactly. So that's a problem with, you know, and you can imagine also, you know, depending on the conditions, things I guess can change as well as to whether, you know, if it is if it's to do with the reflection on water on the ice, if that dries in some way, then you wouldn't necessarily see it again on the optical versus the.
Yeah, it's using this.
Yeah. I think there's biases introduced by the way we've done that.
SAR is half of a quarter of the resolution.
Yep.
In the speckle. Optical doesn't.
Yep.
So it's normally you see more in the optical than the SAR.
Yep.
So, but it would be nice to see how much the algorithm can push be better than a human.
Yeah, definitely.
Okay, so I think we're just after 2 o'clock, so I think we'll wrap it up. But John and Sonny, you're still around, I think, this afternoon for a bit. So so if anyone wants to catch up with them and have a coffee or a chat about galaxies or icebergs
exactly.
or machine learning, I'm sure they'll be around. So just to thank both Sonny and John for coming on.
Thanks.